this on computer. I hope that we have the recording, both recordings. So wow. Let's go back. Well, I have to. I have also to not only Zoom but everything closed unexpectedly. Um, okay, can you see the slides again?
Yes.
Yes, Professor.
Sorry for that. Just the Zoom, not only Zoom, but I also the login shell crashed, so I have to log in the system again. Well, sync. We were here. Sync. Sync is very simple. It empties any cache inside the operating system. So it probably is too strong, but it's the safest one, and provides any kind of syncing between the external hardware, including hard disks, but also communication channels outside, and the operating systems. So the effect of any other writing operation is effective after syncing. You don't have to exaggerate in doing that, because it takes makes the system run slower than usually, because it has to stop to empty the caches and all caches, and then to resume normal operations. Well, here we have a series of other primitives that I don't want to address now and to explain now, but very simple. You can read by yourself. The lseek is important because any file of any kind, including virtual files or communication channels and so on, are sequential channels, a sequential series of bytes. So you have a pointer to the last operation. If you write, the pointer goes on. If you read in sequence, but you can move the pointer using the seek, the lseek, that advances the current position of reading writing with an offset and so on. It's very simple. So if you have to read several times from the same file in following some logical sequence, you can use the seek. Link and link. So these are primitives to create. So I think you can read by yourself these and understand these primitives. They can be, they are the counterpart of shell commands for when you create a new file. You touch a file, create a file, when you remove a file, when you rename, when you move, and so on. And the same for directories, including all capabilities. Read by yourself these slides with the file attributes. You know, I've talked in the video tutorial about the shell, about the attribute, the standard Unix, Linux attributes of the file that are, as a matter of fact, they are POSIX attributes, as to say the capabilities by the owner, by the group owners and all other users to use a file. And usually capabilities are reading, writing, and executing. I didn't tell in the tutorial. I'm smiling when I say tutorial because it is a self-made tutorial, but the execution capability is clear for a regular file, because a file can be a text source, a text file, or an executable file. For directories, execution of a directory means listing the contents of the directory. So it's the same capability, but with a different meaning. We go on. This is very important. I wanted just to come directly to this, because I want to shorten this part and to let you do some exercise. This is very, very, very important. It seems to be, well, nice system call, but some curiosity, solve some curiosity, because it generates an alias of a file descriptor. So alias means that you give a second name for the same object. Well, maybe interesting, but it's very, very important for a mechanism that is called redirection. So dynamic redefinition, dynamic new definition of a file, of a communication channel in particular, between processes, for example, during the execution of the program. It generates, if you have a file descriptor, so we have an open file, you can ask for a duplicate, as to say, a new file descriptor that has the same meaning, as to say, points to the same file. -1 if error, if of course. So we can depict this fact in this way. There is a file descriptor table. We will see when we talk about files that file descriptor table and file table are two components inside the kernel. So we will, the final enrichment of the scheme of the kernel. Here are files. For example, in my process, file descriptor 0 points to a certain file in the file table. And file descriptor 2 points to this. This is the number of, is not the name of the file, is the number of references to the file itself. Files are simply, have no name in this case. You can think of file here, file 1, file 2. If you ask a duplication for 2, you will have the duplication of 2 is this one, number 1. Why number 1? Now you have 2 file descriptors. Both file descriptors point or mean the same file. In that case, the file is this one, and it has number 2 to remember that there are 2 references. But why this one? Because the semantics of the duplication of dup is that the system assigns you the first free file descriptor. A free file descriptor is an integer number which is assigned to nothing. This is very important, and you will see in programming how it is used to that, because you are sure that you can trust on the fact that after asking dup, you have this file descriptor, because how you will use that? You will use you will see that, suppose that you had previously the file descriptor number 1 and you decide spontaneously to close it. Closing number 1 means that number 1 has no meaning, it becomes free. And so if just after, immediately after you do this, you are sure the number 1 is reassigned to 2. So it's deterministic. It's not a random choice of the kernel. So you can decide which is, even if it seems complex or tricky, you can decide which is the new name of the file descriptor. You will see how to use that. Here is a series of system calls for creating files and so on. Some of them will be, I will say something more talking explicitly of the concept, abstract concept of file. An important thing to remember, and you will have also an exercise on that, that files are not, do not include automatic and mutual exclusion. So they are a shared resource and race conditions are possible. That jamming means that if two processes write on the same file simultaneously at the same time, they probably will produce a jam of data because there's no mutual exclusion. There is a way of using mutual exclusion primitives, and in particular, at file level, there are possibility of having the semaphores. You will learn semaphores in real time if you don't know yet in the real-time course, but we will use very briefly. But it's the main theoretical principle of mutual exclusion when you have shared resources. And so the primitives, but we postpone this when we at the moment in which you will have an exercise on that. So you can lock fundamentally. The idea is lock. Your process can become the exclusive owner for a while of a whole file, an abstract file in general, or a whole part of the file, for a record of the file, some part of the file. The owner, the only owner. So any other process trying to access the same file or the part of the file that is locked is blocked until you release the lock. And this is a mutual exclusion service provided directly by the kernel. This is theoretically very important because it is not, it must be explicitly declared by the POSIX standard that this is the mechanism that guarantees you the mutual exclusion, because otherwise you could not write a process that access the same files. So there is a synopsis, and I think that we postpone also this. I want to go directly to the last primitive for now, so that I can ask you to solve an exercise in groups. But it's very simple and easy and quick because we have encountered this primitive in other, also in the overview of the kernel and the exercises you have seen. The fork, you know what happens. Fork just duplicates the process, generates a son. Oh, figlio. Figlio is left from the Italian version of the slides. Means son, of course. And everything is duplicated. Now we can clearly say that in the user area, file descriptors obtained by opens before the fork are in the user area. So both father and son share the same open files. This is the first, the basis of the inter-process communication. The text is not duplicated, you know, because the text can be shared. And so, fork. You know how it works. To the son, it gives back the value 0. the father, the process ID of the son, and in case of error, -1. This is an example, a sketch of example, but you already know perfectly. You know what exec does. Exec has a path name because it refers to the executable. Arguments are those arguments passed to the executable using the standard interface argc argv. And in that case, user area and stack are preserved, but data and text are substituted by data and text of this process. But also in this case, in the user area, open file descriptors are known by both are known after the exec only by the new program, but are exactly the same that were known by the father process. In that case, there is no father and son because the son substitutes the father, but the user area remains the same. Is a family of exec with the only difference in the way in which is implemented the interface for passing arguments. Then, wait suspends the calling process until one of its sons terminates and returns the process ID of the terminated son, -1 if no sons, and gives back the exit status. You remember that when exiting the process returns the father and exit status that is an integer value. You can, this is just, the first one is specifically for the son or the sons, and the wait PID is more general, so you can wait the termination of any process provided that you know it's PID. Exit, you know already the exit, clock times, it doesn't matter, so you know, well, the sleep. Okay. For now, I think it's enough. I would like to, after a 5-minute break, I would like you to solve a problem. And so if there are no questions now, we will break for 5 minutes and we will be back. Otherwise, if you have questions, just ask questions. Okay, so if I stop sharing, I pause. I forgot to start recording again after the pause, but in a few minutes I was not recording, just commented the exercise of last week. So those of you who watched the recorded class do not have this explanation, but it's very not so important. Now, what is important? I want you to solve now in 20 minutes or 25 minutes in groups the following exercise. That is in Aula Web, so you can find the text in Aula Web. I have to share. Okay. Yeah, why is it not here? Okay. This file is well, the text of the exercises is here. The rest of the text file is just an example that you can use to be inspired, or to use the include, or the just to copy and paste some lines of code to have the correct syntax, because it's a main with forking and so on. So the exercise is just create two processes. The first process, you decide which is the first, of course, is not defined. One of the two processes waits until the second dies or terminates and returns exit status from the second. From it means the second. So just this to write the code, generate the two processes, make the second process to show that is alive. For example, writing a loop so that periodically for 10 times or 5-10 times just after 1 second delay, for example, in loop, declares that the second process is alive. And as soon as the second process dies, the first one becomes aware and as the exiting status and prints the exiting status. So do that. Write, compile, execute. I think that using these lines of code it would be very simple to do that. This was just 2 years ago. It was the first question in the first compulsory assignment, but there were many other questions. So after this class, I assume that you are able in few minutes to solve the problem, to write correctly and execute a process like that. Is it clear to everybody? Can I put you on groups and solve this?
Yes, Professor, it's clear.
Okay, I stop share. Retrieve your file from our web, and I okay. 25 minutes. Okay, welcome back. Did you see the solution I put in our web?
Yes, Professor.
Yes.
Okay. Hope it was similar to, well, it's just one possible solution. It's a question of style and so on. But I hope that you succeeded in doing the same program and executing. Is some of you has some question about the program or the code?
Yes, I have a question, please.
Yeah.
What's the return value of wait PD? It's the PID of the process that we are waiting.
No, the wait PD, the return value is the exit.
Sorry, not the return values, status lock.
The status, yes. Well, the status lock.
Yeah, in the slide is written status lock, stat lock.
Yes, is the, let me see. Let's see, just a while. Sorry, where is Zoom? Okay, Zoom.
56.
Yeah. Okay. No, 60 is not another. Okay. Oh, the pointer to stat lock is the exit status. Okay, should be okay. Is not return value. Okay, fantastic. Process ID returns the PID of the terminator son or minor sign stat lock the son exit status. Okay, so returns the process ID of the terminator son. Well, why returns it is returned the process ID? Because it is possible there are more sons more than one. So it returns as soon as the first son exits. In that case, the return value shows also which is the one that has exited, and the exit status is returned by the pointer stat lock.
Okay, thank you.
That's the reason why there is also the return value.
And in wait PD is
In that case, you know the process ID
yeah,
that
this
you're waiting
PID.
for. In the
Okay.
previous case, you didn't know the process ID you're waiting for.
Okay, thank you.
So it was a really basic exercise. Next one tomorrow will be more complex, but you need some other information to carry out to solve the next one. Good. We don't do pause since I want to say something. If this is the case, we will we'll finish 5 minutes in advance. But I want to tell you something about files. Stop share. Okay. I want you to know something. So I will anticipate the second pack of slides, and and tomorrow we will face them. To do that, I will go inside files. No, not here. Okay. Can you see the slide? The part 2 files?
Yes.
Yes.
You can. There is something doesn't work in my Zoom because I have a strange interface. Let me see again. I see one of you. Well, just a moment. I cannot go back to the. To the main screen. Oh, really? I cannot. It does not react. let me try again. Okay, now it works. I'm sorry, I think I have to exit Zoom and going back again because I can't return to the main window. Let me try this way. No. I exit and get back.